All right, you guys, today we are going to be looking at what's called limiting reactants. And I'm going to go through some problems with you. And I feel like this is the best format to do it so you can pause it and try the problems yourself as we go along, see if you know what you're doing. So first things first, let's talk about just like a real world example that would make sense to you without using much chemistry at all. So let's write a generic reaction for how you make a peanut butter jelly sandwich. Okay, so I'm going to put in here, hold on, I got to get color for my pen, and it's being sketchy. Okay. All right, let's do this. Okay, so in my peanut butter jelly sandwich, I'm going to have peanut butter, I'm going to have jelly, and I'm going to need some bread, right? And all those together make my product of a PBJ. Okay, so here's my question to you. So we're starting to talk about this thing called limiting reactants. So we know that the substances on this side are called the reactants, right? I'm just going to put that for short. And this is our product, yes? Okay. So in this case, when I'm asking you about the limiting reactant, I'm asking you about the one that would run out first before you can make more product. That's what the limiting reactant is. And as the example says down below there, it controls how much product can form. So out of our peanut butter, our jelly, and our bread, what would you say your house runs out first? Now, if it was just me, it would probably be peanut butter because I love peanut butter, so I'm going to put a lot on there. I'm going to eat peanut butter while I'm making it. It's not just going to go on my sandwich. But I think most people, their limiting reactant is the bread. Because if you think about it, and I'm going to label that as our LR, if you think about it, bread only comes in about 12 to 14 pieces of loaf, and that only makes 6 to 7 sandwiches, right? And I believe peanut butter and jelly can make a lot more than that. So if that's the limiting reactant, we would then label these guys right here as the excess, and that's how I always label it. Okay, so that's kind of like the really simple way of talking about the limiting and the excess reactant. So now let's go into some calculations. And there's the definitions. Sometimes people will call them limiting reagents and excess reagents. It means the same thing. It just sounds a little more official. So that's the same idea. Just a different way to say it. All right. So big picture thought here. It says, why do you think this concept is important in chemical industries? So when you're manufacturing things like prescriptions or polymers, like all the plastics we use, or fertilizers that we farmers use, why is this limiting reactant concept a big deal? Okay, so what I hear you guys saying is the reason it's a big deal is when industrial chemists have to figure out how to synthesize and make these products, they want to maximize how much product they can produce versus, they don't want to have a lot of waste. In some of the reactions that you'll do, especially if you get to organic chemistry, there'll be reactions where you have like a 30% yield. That means you have 70% waste, which is ridiculous. So you can imagine a product where there's that much waste, it's going to be expensive, right? Because you have to pay for all that waste as well. So just something to think about. Okay, so speaking of fertilizers, ammonia is one that's used in synthesizing fertilizers. Here's our first reaction. So how many grams of ammonia, NH3, can be produced from a reaction of 40 grams of nitrogen gas with 75 grams of hydrogen gas? Okay, so the first thing we have to do here is write our reaction. So I'm going to flip this so that I can write on this. Okay, so hold on, let me pick my pen again. Okay, all right, so there we go. So we have, maybe if it'll let me write, there we go. N2 plus H2 yields NH3. Now, before I can do anything here, I have to balance this. So let me take a minute to balance it. So we know we have a 3 and a 2 here, so let's make them both equal 6. So that's going to be a 3, that's going to be 2, and this is already 2. Okay, so we're good. Now, in this situation, I also like to write below what I have. So I have 40 grams of this, and I have 75 grams of this. And you know what? change this. I actually changed this to 75 grams earlier, and I forgot to change it on this. So they're both the same. Okay, and what we're trying to figure out is how many grams can we make of that? So what you have to do is you compare both of these to the ammonia, and you're looking to see which one produces the least amount. And whichever one produces the least amount is the one that is going to be our limiting reactant. Okay? So we're going to start off with our 75 grams of N2, and we're going to do some dimensional analysis here. We never like to work in grams. What do we need to convert to? For you guys that said moles, good job. So we know that 1 mole of N2, if we look on the periodic table, is 28.02 grams. And I'm going to try to be consistent and use 2 decimal places for everything here. So just as a heads up. Now, and this next step, this is called our mole ratio. Okay, I'm going to put that here because we are comparing the nitrogen to the ammonia. So we have 1 mole of nitrogen in our reaction, and we have 2 moles of ammonia. And then it wants to know how many grams, right? So we have to continue here. So we have to continue on. So 1 mole of ammonia, and I get it on the periodic table, I add it up, is 17.04 grams. And if I multiply across the top and divide by the bottom, this is going to give me 91.22 grams. Okay, that's how much. Okay, so I also didn't update some of these numbers down here. Sorry, I added some things after I loaded it to Word. So let me just change them as we go. Okay, so that's how much we can produce with the nitrogen, but how much can we produce with the hydrogen? So we have the same process. So if you want, you can pause it right here and try it for yourself. So we have 75 grams of the H2, and we're going to try to figure out how much ammonia that produces. Okay, and it looks like a Z. I'm sorry, that's a 2. All right, so 1 mole of H2, we're going to change that to grams or to moles by dividing by its mass. Then we're going to use our mole ratio, our reactions. We have 3 moles of H2. Sorry, this is messy. To 2 moles of NH3. And then this last step's the same. We're changing NH3 to grams. Okay, so now when I multiply and divide, I got 421.78. Okay, so since this one gave me the higher amount, this is our excess. That means some will be left over. Once we make 91.22 grams, the nitrogen's all gone. So that's why the nitrogen is our limiting reactant. Okay, so that's how it works. So you look at the 2, whichever one gives you the lower value, that's the limiting reactant because it produces the least amount of product. Okay. All right, now I'm gonna erase all this because it's in the way for the next part. Okay, so you can pause it if you need to get this. But let me erase all this. Well, I'll erase from here down. Okay, so we got 91.22 grams. Now, I got to change another number here. I apologize. I didn't change it on this document. I changed it on the other one. On Canvas, it is different. So you guys are probably going, why does she have these numbers? Oh, because I forgot to change it. So let me just change this number right here to be, okay. All right, so now let's talk about actual versus theoretical yield. So when we just did that calculation, would you say that was an actual yield or a theoretical, and why? Did we actually make ammonia? No. So the actual yield is from the lab, from lab results. Okay, and theoretical is paper calculations. Okay, so that's something to keep in mind. If you didn't actually produce it, or somebody didn't say this much was produced in the lab, that's not the actual. So percent yield, I think of it like this: percent yield equals at actual over theoretical times 100. Okay, so we're going to try that with what we have here. So we said that our theoretical yield, which we calculated on paper, was 91.22 grams. Remember? That's how many grams of ammonia we said we could theoretically produce. But some chemists in the lab did it, and they got 90.35 grams. So we want to know, what is our percent yield for this? So we're going to take our actual 90.35 grams divided by our 91.22 grams times 100. And we're going to calculate our percent yield to 2 decimal places. And I got that it's 99.05%. Now, some of you guys might be like, well, what's a good percent yield? It depends. It depends on the reaction. Like, again, in some of the organic labs you'll do later, if you go on to higher level chemistry, again, a good percent yield might be 30%, depending on the chemicals you're using, just the way they react together. Okay. All right, so the next question is asking, how much excess remains? Well, let's go back up. Who did we say was the excess? Do you remember? So the excess, if you look at it, the excess was the hydrogen, right? So let's just put that up here so we have it. Use excess, use limiting reactant. Okay, so what we're going to do is the way you calculate the excess remains is you take the limiting and you compare it to the excess. I'll show you what I mean. So our limiting reactant was the, what's it called? The nitrogen. So we're going to take our 75 grams of nitrogen, and instead of comparing to the ammonia this time in our reaction, we're going to compare these two. Okay, so let's do that. So we have 1 mole of N2. We always have to change it to moles. It's 28.02 grams. And now is where we do our mole to mole ratio. But again, we're not comparing the products this time. We're comparing the reactants together. So if we look up here in our reaction, we have 1 mole of nitrogen to 3 moles of hydrogen. Okay, and we don't want it when it says how much, they usually want that in grams. So we need to continue on to get the grams here. So 1 mole of H2 is 2.02 grams. Okay, and when I calculated this, I got that it was 16.22 grams. Okay, now what is this telling me? This is 16.22 grams of hydrogen. That's how much is used up. Because once all the 95, that's our limiting reactant, is all used up, that's how much hydrogen was used. Okay, well, how much hydrogen did we start with? Well, we started with 75 grams. Right, and if we used up 16.22 grams, how much do we have left? We have left 58.78 grams. Okay. All right, so those are the things that you are going to have to be able to do for limiting reactant problems. And I mean, that's really pretty much most of it. So I want you to take some time and try the other problems on, we have example 2. And I said try this one before next class, but I really think you should try both of these for your next class. Okay, because I think it's going to be better to try 2 examples. And then what we'll do is next class we'll go over them. We'll go through those at the beginning of class, and I might pick some of you guys to be able to do them, in front of the class. Okay. All right, so good luck working on these 2 problems and also working on your pipette project, science pipette project. All right, see you guys later.